Okay, so we're going to be talking about limiting reagents. We briefly talked about it last week, but it was a really quick, so I want to kind of touch base on it. Um, and we've kind of done this in lab as well too, so that should kind of help out a little bit for us. So when we talk about limiting reagents, what we're talking about is that one of the reagents, sometimes we have more of one reagent than we have the other one. And so the one that we have the least of will basically run out. So I gave you guys an example of bread and cheese. Let's say we're making cheese sandwiches. So if I have 8 slices of cheese, and then I have, let's do 7 slices of bread. Okay, so and our sandwich is it's going to be 2 bread. I'm going to use B for bread plus 1 slice of cheese, so 1C, and that's going to give us our sandwich. Okay, so if that's the case, how many sandwiches can we make if we have 7 slices of bread?
We could make three full sandwiches, but if we want to be cheap or have a little sibling, you can make a little half one and just fold the bread in half.
I guess we could do that, huh? Yes. So because we know the bread is going to actually run out before our cheeses will. So like you said, we'll be able to make 3 full sandwiches, and if we want to be really cheap, we can fold one of them in half, right? So that means that our bread is going to be limiting, and our cheese is going to be in excess. Okay. So, and this is what normally happens in real life. It's like often you have more of one product than you have another one, uh, for whatever reason. So you're going to be limited by the one that you have the least amount quantity wise. Now, this is going to be really important to pay attention to in chemistry because often we want to look at it in terms of mass, but we can't be looking at it in terms of mass. We've got to be looking at it in terms of quantity. So we want to make sure that we're looking at the number of moles instead of the grams. Okay. And I'll show you that here in a minute. Okay. So now this is just an example showing you what we're talking about. So here we have 3 carbon and we have 2 oxygen molecules. So for us to make carbon dioxide, we're going to use one of the carbon, I mean, you're going to use 2 of the carbons, and then you're going to use 2 of the oxygen molecules, meaning that your carbon is going to be unreacted. It's going to be left over. Okay. And this is just basically showing us that the moles that we started out with, and then this is, we often will call it an ice table, where it's the initial, what we initiate it with, what we end up with, and then normally be equilibrium. But for us, it'll be the final thing that we get after the reaction, right? So in this case, we're going to be using, since there's a 1-to-1 ratio, we're going to be using up 2 of those moles of carbon, and you're going to be using 2 of the moles of O2. And so then that's going to give us 2 moles of CO2. Okay. So recognizing that we have, anytime, let me take a step back. Anytime that you have a value for 2 products, I mean, for 2 reactants, that means that you're going to be using a limiting reagent. One of them is limiting. Okay. So in this case, it says calculate the mass of antimony 3 iodide, which is SbI3. That can be reduced by the reaction of 129 grams of antimony, Sb, and 381 grams of iodine. Also, find the mass in grams of the element that will be left. Okay, so that's telling us immediately that we're going to have something that's going to be left over. So the very first thing that we want to do is kind of figure these guys out. We have them in grams. And we also need to probably pay attention to what as well. What is it that we're missing that we can figure out? Any ideas? What are we missing? What is the first thing that we should probably figure out? Any suggestions? How about a chemical equation? Do we have a chemical
Yeah,
equation?
we
Okay.
have one antimony with three iodide.
Okay. So we have SB. Well, that's going to be our product, right? SBI3.
Oh yeah,
Yeah. So that's going to be our product because they tell us that can be produced by. And so then our reactants are
reactants are SB and I
SB plus I.
plus I.
That's right. And we know that I is what? Is it
It's
monatomic, diatomic, polyatomic?
diatomic 2.
Okay, that's right. So we need two of them. So it's diatomic. Okay, so is that balanced?
No,
No, what do I need to do to balance it?
we could put a let me think. So we got SB, I, one SB on each side, two iodine on the left on the reactant, and three on the product. So we could put a three on the I and two on the SBI3, and then put another two on the SB to balance it.
Okay. Okay. So now we have a balanced chemical equation. Now we know that when we look at this, this tells us that for every two anthymies, quantity two, we have three iodine molecules, and that's going to make two anthony 3 iodide. Okay. So we know that these represent quantity. So we need to figure out the quantity of everything. So how would I figure out the quantity starting from the mass, which is the weight? What will I need to do?
So we're going to use Avogadro's number
Are we going to
or
use Avogadro's number? Because we have mass.
or
Avogadro's number is
mass.
quantity and moles. Right? So what are we going to use since we have mass?
Probably the amount of moles compared to the other element.
Okay. So how do we get to that? You're jumping a couple of steps.
Oh shoot.
So what do you know about anthony? Where can I
And
find out information about anthony?
in the in the worded question.
Well, in the worded question, what does that 51 stand for?
Oh,
Do
I
you remember?
can't see the 51.
Oh, because I'm in the way now.
There's a window.
There we go. Sorry.
That's
What does that
yes,
represent?
and represents C. Oh my goodness. It's been too long today.
I know it's been a long day. So let me see if I can help you out. So that Z represents the atomic number.
Oh,
Okay. So if we're talking about the atomic number, we're probably going to be looking at what?
the protons, neutrons, and electrons.
Are we going to be looking at the protons, neutrons, and electrons? I
No.
mean, although that's what it tells us, but there's something else. What are we going to do to find out about Anthony based upon his atomic number? Let me see if I can help you guys out. So we're going to take a look at Anthony on our periodic table, right? And we're
Yeah,
going to
it's
get 51, right? That's Z. So how much does it weigh?
121.76
What are the units for that?
AMU, or you
Or,
can use U or MU.
or if we have a lot of it, if we're working with it with our hands, are we going to be using atomic mass units? Or are we going to be
No,
using
grams
grams per what?
per mole.
Grams per mole. Okay, so anytime that you see grams, you know that you need to be using grams per mole because that's going to allow us to get quantity, right? And moles represent quantity. They represent a large bundle of quantity, kind of like a dozen represents 12 donuts,
You
right?
know what's funny, Professor?
What's that?
I was just doing the slide on for stoichiometry on moles and grams
Oh, really?
at 3 in the morning.
So you're like, man, I should know this. It was just what I just did. Okay, so we got, what did we get for Anthony? 121, you said?
Yeah, 121.76.
Okay. Yeah, that happens when you're kind of brain dead, from working so much, not enough sleep.
And when I was serving myself, because it was Teachers Appreciation Week at the center,
Uh-huh.
I grabbed the bowl upside down and almost started to pour it. You know what pozole is?
I do know what pozole is. I love pozole.
Yeah, I almost got like I started serving myself the bone chunks too once I flipped it over.
Yeah. Okay, so now we have our number of moles. Now, so the way that we can determine, there's two ways, there's multiple ways that we can consider. We can figure out how much of the other one we're going to need. So we can figure out how much of the other reactant we're going to need and determine how much we actually have. Or we can sit there and just determine how much, um, sorry, how much of our product that we can make. And so the one that makes the least is going to be the one that is going to be limiting. So in this case, let's just go ahead and try to look to see how much product we can make, the number of moles that we can make with our product. Okay. So if we go ahead and do that, it'll be for every 1 mole, I'm sorry, for every 2 moles of anthony, we have 2 moles of our SB. So, okay. So here, our units are going to just cancel each other out. Okay. So then we'll do that calculations. My calculator here.
And we're using sig figs.
Yeah, let's do sig figs. We're going to have
All
three
right.
sig figs, right? Because that's what we're starting off with.
Should it be like 2.10 because the point 2.12 doesn't matter, the 0.02?
The, I'm sorry, hold on.
Because it's 2.118. So I'm trying to remember the rolling for sig
Oh,
figs.
so we're going to be rolling up. If it's exactly five, if it's greater than five, we round up.
Oh, okay.
So you got 2.13.
Oh, it's 2.11, and then the 8 is the fourth digit.
How did you get 2.11?
Uh,
129
let's see.
divided by 121.76 times
What's
2.
going,
Oh, yeah.
what's
Okay.
going
2
on
point.
today?
Don't worry
Was it
about it.
right?
You go. Yeah, you're right.
Oh, okay.
2 point. So it's 2.118. So then that'll be 2.12. And that's moles
SBI 3.
SBI3. Okay. And then we're going to compare if we started out with our iodine. Okay. So we know that our iodine is I2. So each iodine is 126.9. So we have 126.9. And we get that again from our periodic table. Let's see.
Shouldn't it be 253.80?
Okay. Okay. So we're going to. Okay. So then we're going to go ahead and use that. So 253.8 grams per 1 mole of I2. Okay. And then we know that the relationship, get our periodic table out of the way. So the relationship is 3 iodine to 2 SbI3. So for every 3 iodine, we're going to put the iodine on the bottom, 3 moles of iodine. We have 2 moles of our SbI3.
All right.
Okay, so let's go ahead and multiply that.
Well, this is just straight one. There's too many zeros.
So you get 1.0.
0 moles.
Okay. Okay. So that means which one is going to be limiting for us? Which reactant?
The iodine.
The iodine. Okay. So we're going to label it as limiting. Okay. So now they want us to find the mass of the iodine that we're generating, I mean, of the SbI3 that we made. So we're going to go ahead and use that 1 mole. So we're going to do that over here. Put in a different color. Part 2. Part 2 is going to be green. So we have 1.00 moles, and they want mass. So we want grams. Okay, so we know the anthony, we have 1 anthony, which is, we know that that weighed 121.76 grams. And then we had 3 iodine, and then that weighs 106. I mean 126, sorry.
Probably 0.90.
126.9, and we're multiplying that times 3. Put that in a different spot.
So that should be 380.70.
Okay. Okay, so when we add that all together, is that this one is 380.70. Okay. And then we're going to add that with the 121. So we'll do it over here, 121. I hate when I run out of room. 121 grams plus our 380. 70.
Should be 422.46 grams.
You said 4.
22.46 grams.
Okay, are we sure? Hold on. See, 126, 126
Wait,
point
don't forget to carry the one.
3. Yeah,
What?
so it's 380 plus 121.76.
Oh, that's 522.
Yeah, so we're a little off there.
I'm so glad I'm not working at McDonald's anymore. Being a cashier for getting the 10. I know a coworker who didn't give a 10 to a person, and they're like, man, my wallet feels very light today. And they look at the receipt and the change they're given, and
Uh-huh.
then they're mad at the my coworker who I let on my break on my register.
Uh-huh.
And they're upset, yelling at the manager. The manager is yelling at me. I'm on my break, and I had to tell the manager, who's working the register? Well, I'm sitting here. And then she looks at the back as the person that's not supposed to be on the register that she pointed to go to work on my register while I'm on my break.
And that's grams per mole, right?
Yes, grams per mole.
Okay, so now what we're going to do, we want to get rid of moles. So our moles are going to be on the bottom. That's an SBI3. And then on top, we're going to have that 502. Okay, so which we know is just going to be 502. Okay, so there's a couple of ways that we can do this. Now we found out how much mass that we have, right? So we can sit there and we can calculate how much SB that we actually used. Or what we can do is we know that the total value is going to be 502.46, right? So the rule is what we put in, we have to get out. So this is how much we put in that got reacted. So whatever's left over is going to be what was that out. So what we can do is just add the two together. Add these two together, and then we just subtract our value here. So if we have, let's see, what is it? 129 plus, oh, and actually, if we should do 3 sig figs since we have 3 sig figs, so it'll be 502 grams.
Okay.
Okay, so we have 129 plus 381, and then we're going to subtract 502. And so that should give us the amount of anthony that wasn't used.
That's about 8 grams
Okay,
of antimony.
so we end up with like you said, approximately 8.
That's I put in the calculator 129 plus 381 minus 502.
Yep. So it's actually 7.54, but yeah, 8 roughly after we get the number of sig figs. Well, since this was all added from this, so then we get 8 grams approximately SB. So that is one way of doing it. The other way of doing it is after we figure out our mass, how much we can make, we can use this number to calculate how much anthony that we used, and then we subtract that value, right? Which is the same way around. This is much easier than in the other case. So, okay, let me clear. Okay. So the next thing that we're going to be talking about is solute and solvent. We've already kind of talked about this before. We know the solute is basically going to be what we're dissolving in. So it can be a solid, it can be a gas that's dissolved in some type of liquid. The solvent is what we're using to dissolve the solute. So for instance, we have copper, I believe this is copper chloride. So since we have copper 2 chloride, um, we put the copper 2 chloride in there and it actually dissolves in solution. So we end up with the copper ions and we have chloride ions in there as well too. And so in that case, you get this nice, beautiful blue water as it dissolves in the solution. Okay. And this is just basically showing you that it actually will dissolve and it'll form its ionic components. So when we talk about something being concentrated, it's just basically we have a solution that has a large quantity of the solute. Um, and then diluted basically means that we have a small quantity of the solute per amount of solvent or solution. So here's an example. This is basically a diluted solution, right? And so in this diluted solution, this here is the copper wire here, and then we have silver nitrate. I usually do this experiment in class, but we're running out of time. So this is after a small short time, and so you get the silver forming on the outside of the copper wire, and then here in this situation, we actually have the silver forming on the copper wire, but it's super concentrated that you get a lot more silver that is starting to form. And then so some of the ions, the copper ions, which is causing it to interact a little bit with that silver, they're weakly interacting with each other to give it that kind of greenish color rather than truly silver looking. And so this is an example of a diluted and then a concentrated solution. Okay, so ways that we could sit there and calculate concentration, right? So we're always looking for ways to calculate concentration. So one ways that we can calculate concentration is by mass. It's called concentration by mass. So in that case, we're going to have the mass of the solute divided by the mass of the solution multiplied by 100. Okay? And so when we do this, we always make the assumption, right, that we're multiplying it by 100 because we assume that we have 100 grams of our solution, right? Okay. And in the case of, again, our solution is going to be composed of our solute and our solvent. So,
Well, I didn't
so
get the last equation for the other one.
I'm quick. Quick to the draw.
All right, solute and solve it. All right, thank you.
Okay, so when we have 125 grams of our solution, 125 grams of our solution was evaporated to dryness, and 42.3 grams of solute was recovered. What is the percentage concentration of the solution by mass? Okay, so what are we going to do?
Since we're doing the concentration of the mass, we're using the first one, which is mass over solute and mass of. Oh, I didn't write that good. I think it was solution. Solution, yeah, solution times 100.
Okay, yeah. Mass
So
of
our
solute.
42.3 G over 125 G times 100. So that should be 33.8 with sig figs.
Okay,
That's percentage. I almost wrote G. I was like, look at the question. Wait a minute.
no, you said it's 42.3 divided by 125 times 100. And you said it's 33 point,
8.
excuse me. Okay, so you're prepared. You are to prepare 2.50 times 10 to the 2 grams of 7% by mass sodium carbonate solution. What is the mass in grams of the sodium carbonate, and what volume in milliliters of water do you use? Okay, so we're going to be making our solution here. Okay, so they want us to prepare 250 times 10 to the 2 grams of a 7% by mass. Okay, so we know how much solution we have. That's our solution. We want to find our solute, so we're going to put sol for short for our solute. And that's going to be multiplied by 100. And that's going to be equal to 7.0%, 0.00%. Okay, so that means if we solve for sol,
We can divide by 100.
okay, so we divide both sides by 100. Okay, so then the 100 cancels out over here. And then Okay. And then if we want to get to solid by itself,
We multiply the 2.5 by 10 to the power of 2, which is 250.
okay, so we multiply both sides by 250.
And since Sol is in grams, it should be 17.5 grams.
Okay, so then that 250 is going to cancel out the 250 down here. And so you said it's going to be equal, Sol is going to be equal to, what was the
Oh,
value you said?
17.5 grams.
Okay. So that's how much solution solute that we're going to need. Okay. So then how much water do we need to add to our 17.5 grams? Now we're going to make the assumption that the density of water is 1.00 times 10 to the.
So we're going to need 17.5 milliliters.
Okay. So now this is of our solute. So this is
Oh,
going to
it's
be okay. This is
oops.
going to be of this is going to be our sodium carbonate.
Okay.
Okay, so now we know that we had 250 of our total solution, and we know that 17.5 of it was sodium carbonate. So if we go our 250 minus our decimal point there, so we know that we have three sig figs minus 17.5 grams, and then that's going to give us the grams of water.
Oh, okay. So 232, and then since it's the 5, just keep it so it's 232 grams.
Okay. Okay, so then now we know the grams, and that's of H2O. So then we can use that 232 grams of H2O, multiply it by its density, which is 1. So you get for every 1 gram on the bottom, oops, we get 1 milliliter. So it's just 232. Ugh. Okay, not too bad.
A little bit.
You said a little bit. So we're both exhausted, it sounds like.
Yeah. I had a nap on the bus on the way home, so it shouldn't have been that bad.
Okay, so molarity, and that's the unit that is most commonly used is molarity, and that's moles of solute over liters of solution. Okay. So in this case, we're getting the quantity over in a volume, right? So it's moles of solute over liters of solution. So calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting to 1.00 times 10 to the second milliliters.
Oh,
Okay. So,
I don't mean to be rude, but I was just barely jotting down the equation.
oh, I'm sorry.
All
I'm
right.
clear. Sorry.
Solute and liter solution. All right.
Okay.
Yeah.
Okay. So calculate the molarity of solution made by dissolving 15 grams of sodium hydroxide in water and diluting to 1.00 times 10 to the second mils.
All right. Mass. So 15 over 1.00 by 10 to the power of 2.
Okay, now remember we're talking about molarity,
Oh,
right?
molarity.
Which again, molarity,
Oh, shoot. Gotta go to the periodic table.
yeah, we need to go to the periodic table. Okay, so let's go to the periodic table.
We have one Na,
Okay, so we got one Na,
22.990. One O is 15.999. Then we got a H is 1.008.
we're gonna be a little since we're tired
A little
and
quick
working all day,
today. No more decimal.
we're gonna go make that 23. And then the oxygen, we're gonna make that
16.
16. And then the hydrogen, we're gonna make it one.
So one.
Because we got one of each, right?
Should be 39. I don't know how, but I can just do addition.
You mean 40?
40?
Yep.
Oh, 23. Okay. Yeah, 40.
Okay, so
All
it's
right.
grams per mole.
40
Okay.
G of AOH.
Okay, so then we need to change our 15 grams into moles.
Oh, that means we should. To 1 mole. And this should be 15 G. I don't know if you can hear that, Professor, but one of my neighbors got a new motorcycle with his tax returns. And he's riding it down like one of the longest streets in the city, in the little town.
Right.
So everyone could hear it.
You just
He
put
was talking
the
about it for
motorcycle.
some time, so I think now we know he finally got it.
Okay, so it'd be 375 exactly. So 375 NaOH. Okay, so now that we got the number of moles, we're going to divide it by, well, we got to change our milliliters to liters. So we have 100 milliliters. You change that to liters. How do we change that to liters?
So it's, let me look at my little table.
Okay.
So liters, since I know that's like a hundred-ish negative, so if we do that, it should be 0.1. So let me think. So 1,000 milliliters is 1 liter. Yeah, 3 milliliters is 1 liter. Now if I type in the calculator, hopefully I can get the number I'm thinking of. it's 0.1 liters.
Okay, that's right.
All right.
So then we know that molarity is going to be moles over liters. So then we just put our moles over our liters.
All right. This reminds me of the time when they put me into that gifted program and it was like in the third grade and I was already a kindergartner and I was like, okay, we're using this symbol with an X. Like, oh, that's an additional, just printed the wrong way. It was not what it's supposed to be. So 3.75 molarity.
That is correct. If we had two sig figs, it'll be 3.7, and that'll be NaOH. Okay. Let's see. What's next? Okay, molality. Molality is moles of solute over kilograms of solvent. Now, molality is used, it's not used all the time. It's specifically used for when we're trying to calculate boiling points of a solution, or if we're trying to freezing points of a solution, or uh, or vapor pressure, things to that extent. Oh, did you get the equation?
Yes, yes, I got the equation. That was the first thing I darted for.
Okay, so we know that molality is the little n. Molality is going to be equal to moles over kilograms. Okay, so how many grams of potassium chloride must be dissolved in 2.2.50 times 10 to the second grams of water to make a 0.400 molal solution? Okay, so again, molal is basically moles over kilograms. So we can actually change that to just moles over kilograms. And that's going to be 1 kilogram. Okay, we have our solvent. We have 250 mils of our solvent. And that's in grams. So we need to make sure our units match up. How can I convert grams to kilograms?
There should be 1,000 grams in 1 kilogram.
Okay, so we have 1,000 on the bottom then, grams, and then 1 kilogram on top. Okay, so now the kilograms are going to be able to cancel out. The grams are going to be able to cancel out. And so this would give us our moles of potassium chloride, but it wants grams of potassium chloride. So how would I get to grams?
We have to find out the weight of potassium chloride. Not so
Okay,
quite.
okay, so we have 1 and Cl So let's go look at the weight. Potassium is 39.098.
Okay, there. They just need one of each. Cause looking at the charges.
Yep.
All right. Let's see. 39.098 CL35.45.
Together.
Uh, should be 74.548, but sig figs. That is it the four or the five that gets the dropped at in the decimal range?
So in this case, we don't have to worry about sig figs because it's coming from the periodic table.
Oh, okay.
So in a lot
All
of times
right.
they're rounded off anyway. So in this case, we're going to put that we want grams on top. So 74.548 grams on top and 1 mole on the bottom. Okay, so then our moles are going to cancel out. So we can actually see what I'm writing. So our moles are going to cancel out. And then we'll just multiply and get our answer.
All right. 7.454, but I need sig figs. Let's see. I just keep the 7.4, or is it just a 7? Oh boy.
So you have three significant figures. So you should have
Yeah.
three sig figs.
I think it's 7.4. I hope I'm right on the sig figs.
So it should be
Decimal.
7.4. So it should be three sig figs. So it should be
Oh,
7.45.
5.
Yeah.
Okay. That's molality.
Oh, no, now because we calculated
Oops.
grams. That's what
Oh,
we
grams.
went all the way to calculate the grams.
Today's something
Yeah,
special today.
yeah, we got rid of molality early when we did this here. So we changed that molality into moles per kilogram.
Oh, okay, that's molality.
You're funny when you're exhausted. You laugh a lot.
Yeah, I do.
Okay. So we talked about percent mass, we talked about molarity, and we talked about molality. We're not going to talk about normality. Normality is it's a dated unit, and it's basically it's used a lot in old chemistry um, when you're talking about equivalence. So it's another way of thinking about it, but we're not going to talk about it today. We'll wait when you guys get into general chem to talk about that. Okay, so solutions can be diluted by adding more solvent, and there's a quick way of determining this. What we can do is we can have the volume of our concentrated solution times the concentration of our concentrated solution, or we'll call it the molarity or the moles, or not moles, but molarity, molality, any type of concentration that we have is going to be equal to the volume of our diluted of our dilution, and then the moles or the molarity of our dilution. So what do I mean by that? So if we take a look, the yellow represents our solvent, right? And then this here represents, the blue is going to represent like water, okay? So the quantity, we have 1, 2, 3, 4, 5 yellow, is going to be the same here, but we have a bigger volume, right? Because we've added more of our dilutant. So, but the number of moles is going to be the same for both. But these are going to be two different concentrations. This is more concentrated. This one is more dilute. Okay, so when we go about making a diluted solution from a concentrate, what we're going to do is we take our concentrated volume. So in this case, excuse me. In this case, we have 100 mils of 0.1 molar potassium chromate, dichromate. And so we're going to put that in our new volume of 1,000 mils. So we go ahead and pour it in there. We're going to rinse it off a couple of times, and then we're going to pour that into here so we don't lose any of our concentrated solution. And then what we're going to do is we're going to bring it up to volume, right? So after we've done a rinsing a couple of times to get rid of, rinse out all of our concentrated solution, we're going to bring it up to volume so that we bring it up to a total volume of 1,000 liters. I really mean, I'm sorry, 1,000 milliliters or 1 liter. Okay. And so then the new volume is going to be 0.0100 molar. Now, the way that we go about doing that calculations, right? So let's say we want to make a liter of our new solution, of our diluted solution. So we're going to start off with 100.0 milliliters. We're going to multiply that times 0.100 molar, which is our initial concentration. So that equation where we had V1 or V concentrate times M concentrate is going to be equal to V dilute times M dilute. So in this case, we're going to solve for our dilute. So that's going to be equal to, we know that we want to make 1,000 liters. I mean, sorry, 1,000 milliliters, which is 1 liter. So we'll have 1,000 milliliters times our MD. Okay, so then we do the math. We're going to end up, we're going to divide both sides by 1,000 so that we can get M alone. Okay, and then we end up with, I'm going to write it down here.
Point zero zero one.
Shouldn't it be 0.01?
Wait, what did I do wrong again? Right, so we got the 100 times. Oh, point one. Okay. Yeah, that's good. Point zero one. Okay. scribble out the decimal, make a new one.
And that's molarity. So we're going to draw a line underneath it. So we don't just mistake it for M. Okay.
Yes.
Okay. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, should be used to prepare a 5.5 liter of a 0.500 molar hydrochloric acid? So they want milliliters.
All right.
Okay, so we're going to use that equation again, that V D M D is equal to V, oops, C D, oops, M MC. Sorry. Yeah, I'm getting better too, if you can't tell. Okay, so what I always do, I define everything that I have. So it says my dilute volume is what we want to have. So we don't know what that is. So we're going to make that a question mark. Okay. And then our molarity dilute is going to be the one that's the highest,
11.6.
11.6. That's going to be our M. We're going to put a line underneath it. Okay. And then our molarity, oh, sorry, not dilute. That should be C. Sorry. My brain is not working today. D is diluted, so that's less than.
Oh, okay.
Yeah, sorry. My brain is kind of not working. Okay, so then my dilute is going to be the one that's less. So that's going to be our 5.50 liters, which is going to be the same thing as milliliters. If the units always match up, it makes it easier because they'll end up canceling each other out. So we're going to make this, what is that, 5,500 milliliters. If we multiply that number by 1,000,
Let me see. 5.5. Yes. Yes, it is.
okay. So my volume, oh, damn it. I am screwing up today. Let's do this right. So this is our volume because it's milliliters. Our concentration, wow. Okay. And then let me fix this again. We'll get this right. My bad. That's going to be our volume. Our concentration is going to be MD, and that's going to be 0.500 molar. Okay, let me make sure. Okay, so our volume concentrated, we don't know. Our molarity concentrated, it's going to be 11.6 molar. Our volume dilute is going to be 5.50 liters or 5,500 milliliters. Our molarity dilute is going to be 0.500 mol. Okay, so then we want to solve for VC. So to do that, we're going to go ahead and do our equation first, and then we'll plug in the numbers. So we're going to divide both sides by our MC. Okay, so then they're going to cancel each other out.
Hmm.
Here. So then we get, and I'm going to flip this over. So it's VC. It's going to be equal to VD MD over MC. So then we can just plug everything in. Our VD is going to be 5,500 milliliters times our MD, which is 0.500 divided by 11.6. Okay. So our molarity cancels and we're left with just milliliters, which is what we want.
That should be 237. Should it?
Let's check. Check.
All right.
237. And we should have three significant figures. So we're good to go. Okay. On to the next problem. Okay, so when we're starting to use molarity for stoichiometry, um, we always want to try to get to moles. And so we're going to have to use the volume so that we can end up getting to moles. And then once we get the moles of what we got, we want to get the moles of what we want, right? And so then we use the equation to get to the moles of what we want. And if we want to get the mass of what we want, we multiply it by its molar weight. Or if we want to figure out the molarity, we'd have to divide it by the total volume. Okay, so this is just basically showing you what we can do with stoichiometry, right? So if we have energy or heat, we can use that to sit there and calculate the number of moles. And then that can be used to calculate from a chemical equation, we can figure out the products or other reactants. And then we can sit there and figure out the quantity in terms of particles or molecules or atoms or electrons. Okay, but you can do that from either, as I said, energy, mass in grams, your gas, your gas laws, or in the case of your molarity or concentrations. Okay, so here is our example. It says calculate the volume in milliliters of a 0.842 moles of sodium hydroxide required to precipitate copper 2 hydroxide. All of the copper ions in 30.0 milliliters of 0.635 molar iron 2 sulfate. Okay, so our chemical equation is going to be sodium hydroxide reacting with copper sulfate.
CuSO4.
Okay. And then that's going to yield copper 2 hydroxide. So we're going to need two sodiums to balance out the sulfate, which has a -2 charge. And anything that's with um, a group 1 metal is always going to remain aqueous. This one is going to precipitate. It's going to form solid. This one is going to be remaining aqueous. And this one is also going to be aqueous. Okay, so is our equation balanced?
No.
No. Okay. So we have sodium, we have hydroxide, we have sulfate, and we have copper. Copper. Okay. How many sodiums do we have on our reactant side?
Reactants, we have one.
Okay. On our product side,
Products, we have two.
hydroxides. On our reactant side,
One,
on our product side,
two.
sulfur. I mean, sulfate. On our reactant side,
I was about to say zero because you said sulfur. I was like, zero because I thought it was a trick question, but you said sulfate. So
no,
just one.
okay. And then on
One
the
on
other
this
side,
side,
okay. And then
and
copper,
then one on each.
one of each. Okay. So is it balanced?
No,
What do I need to do to balance it?
we gotta multiply the two. We gotta put a two in the NaOH, and then it should be balanced.
Okay. Okay. So we're completely balanced. Okay, so now we can actually start doing the problem. Right? Now that we have a balanced chemical equation. Okay, so it tells us that we're going to be starting off with 30.0 milliliters of copper 2 sulfate. So, and we want to calculate the volume in milliliters of a 0 point that's going to precipitate copper. Okay, so we're getting rid of all of the copper. Okay, so we're going to go ahead and start off with this guy. And we know that we have 30 mils. Of CuSO4. Okay, we have the molarity of it. So what is the definition of molarity? It's what over what?
Let me flip to my notes.
Okay,
Molarity is mass solution over liter solution.
and moles.
Moles. Oops.
Yep.
Moles solute over liter solution.
Okay. Okay, so then we want to put the volume on the bottom, right? But we know that this is milliliters, but we know we need liters. So first I need to change my milliliters to liters.
A
So
thousand milliliters to 1 liter.
okay, so I put 1,000 down here.
Let's see. Oops. Should be 0.03 liters
Okay.
of CuSO4.
Okay. So we have that value, but we could actually just keep going on since we know that the molarity is going to be 0.635, and that's going to be moles, and it's going to be over 1 liter. CuSO4. Okay, so then those liters kind of cancel out. Okay. So then we look at the mole to mole ratio between copper 2 sulfate and sodium hydroxide. So for every 1 mole of copper 2 sulfate, how many sodium hydroxides do I have?
2.
And I get that from my chemical equation. NaOH. Okay. Okay, so then that gives me my moles of NaOH. And then if I want milliliters, I know that I can change that to moles over liters. So we're going to put the moles on the bottom now because we want to get rid of moles. So we have 0.842 moles. And then we're going to put the liters on top. Okay. And then we want to get to milliliters. So how do I change my liters to milliliters?
1 liter is 1,000 milliliters.
Okay. So 1 liter, 1,000 milliliters. Okay. And then we're going to go ahead and solve it. Okay, so let's see what we can get rid of. Rid of that. We can get rid of this 1,000 over here. And that gets rid of this 1,000 over here. So then we're left with, oh, and our answer will be in milliliters. We'll leave those milliliters alone. Okay. So I guess for my 1,000. So then I have 30 times 6.35 divided by 0.82. So that's going to equal, and you should probably check my math, 45.2 milliliters.
Yeah, it's 45.2.
You got 25.2?
Yeah, 45.2.
Okay. We're both exhausted. We're barely holding up here.
I remember I have something in my fridge. It's an energy drink. I'm
Yeah.
debating on drinking it.
Oh, because no, you should probably not, because then you won't go to bed. You'll be
Probably just a little sad.
okay.
Go run a couple miles outside and I'll tire out.
That's right. Burn yourself out. Okay, so one of the ways that we use molarity is that we use it by titrations. So we have these things called burettes, and they basically have the volume of what we call of our titrate. So we're going to basically use that to titrate something that we know is unknown. We often will use a color indicator. Um, it basically changes colors to let us know that we reached a certain concentration in the solution. And it's typically based upon pH in most cases or something along those lines. So here's an example of a burette. And so it's gradiated. And so typically they have various sizes, but the most common one is up to 50 mils. So at the top, it'll say either 0 on one side and 50 on the other. And then as you uh, open up your valve, it'll drop down. And so you would just take the difference of the two to sit there and figure out how much you've added to your solution. And so you basically do this until you get your indicator. Your indicator changes color or um, yeah, changes color or some color appears or something to that extent. So now normally when we're doing our titration, we want to standardize. So we will work with known concentrations and then we'll go ahead and titrate those titrates with the known concentrations to make sure that our standard is correct. And so this is going to be basically our primary standard. And then, sorry, and then we do our unknown after we've done our controls, in a sense. Okay. So a 25.0 mil sample of electroplating solution is analyzed for its sulfuric acid concentration. It takes 46.8 milliliters of a 0.661 molar sodium hydroxide to neutralize the sample. Find the molarity of the acid. Okay, so we should probably write down a balanced chemical equation. So sulfuric acid H2SO4, and plus we know it's an acid, so we're going to put A cubed, so it's a solution. And that's going to be reacting with sodium hydroxide. And we know when we have an acid and base reacting together, we're going to end up getting water. And
Let's see. Um, I think it's the metal, right?
it's the metal, that's right. NaSO4. We call it the salt. And that's going to be AQ for aqueous. And then this is going to be L for liquid. Okay. So now is our equation balanced?
Let me see. We got 2H, one, 4 O's, 5 O's on the left, and 1S. So let me write this. I cannot do this for anything.
You're exhausted, that's why.
1, 5, 2, 1 on the reactant products, 2H, 1Na. See, it's 5O, 1S. Oh yeah, it's balanced.
Are you sure? How many H's do we have?
Oh wait, oops. 3.
Okay.
Forgot about the other H. OH. Okay. Let's see, what do we do about that? I was thinking putting a 2 in the NaOH and another
Oh, yeah, I
2.
forgot the two anyway. So that should be two anyway. There we go.
Oh, there's a 2 there too. Oh no.
Okay, so now we got two here, and then now we have four.
4. Yeah.
Okay, so then what's next? Then we have how
See.
many oxygens now? So that's what, six?
Yeah, we have 6 now. Oh boy.
Start off with the hydrogen.
Let's just do two hydrogens.
Okay.
Two of them for the H2O. That's four.
Then that's
And
how
this
many
is
oxygen?
that's just adding one more, so six.
Okay. Is it balanced now?
Yeah, looks like it.
Okay, so we got our balanced chemical equation. Okay, so what are we going to do next? We want to find the molarity of our acid.
And our acid is H2SO4.
That's what we want. We want the molarity of that guy. So we're going to start off with the other guy then, right? Because we know everything about it. We have the volume and we have its concentration. So this gives us milliliters. So what do we want to do with that? Since the units for molarity is what again?
Molarity mole solution over liter solution.
Okay. So we want to get to liters, right? Since we have milliliters. So how do we do that?
We gotta turn milliliters into liters.
Okay. So we know 1,000 milliliters will equal 1 liter. Then we can use its concentration, which is 0.661 moles per 1 liter. Okay, so then that gives us our moles for sodium hydroxide. So how would I get from moles of sodium hydroxide to moles of our acid?
Let's see, we have two NaOH to one.
Okay, so for every 2 moles of NaOH, we're going to have 1 mole of H2SO4. Good job. Okay, and so that's going to give us our moles. Go ahead and calculate that.
That should be 0.01546, but our we want our three, so we're keeping 0.0155.
Okay, so it's going to be 0.0155.
And that would be moles H2SO4.
Okay, and then we'll take that number. We need to first, oh, sorry, I'm getting ahead of myself. We need to change this guy into liters. 25.0 milliliters. So for every 1,000 milliliters, we get 1 liter. That's going to be 0.025 liters. Okay, so now we can take our moles and divide them by our liters. That's going to give us our molarity. Molarity is going to be equal moles over liters, which is going to be 0.0155 moles. So 4 divided by 0.025 liters.
0.62 for molarity.
Okay, I get 0.619 because we have three sig figs. Oh, I forgot my zero.